Good morning, students. Myself, Vaidegi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today, the video lecture is from the subject EC3452 Electromagnetic Fields. The topic we are going to discuss is from the Unit 5 of EMF. Today, we are going to discuss an important topic in electromagnetic fields, namely normal incidence at a plane conducting boundary and normal incidence at a plane dielectric boundary. Whenever an electromagnetic wave encounters a boundary separating two media, part of the wave may be reflected and part may be transmitted. Understanding this behavior is essential in communication systems, antenna design, optical fibers, microwave engineering, and radar applications. Next, we see about what are the learning objectives. At the end of the lecture, you will be able to define normal incident and explain its significance. You will understand how electromagnetic waves behave when they strike conducting and dielectric boundaries. You will also learn how to calculate reflection and transmission coefficients and solve numerical problems related to wave reflection and transmission. Next, we see about the review of plane electromagnetic waves. Before studying boundaries, let us briefly review plane electromagnetic waves. An electromagnetic wave consists of an electric field and a magnetic field that are mutually perpendicular to each other. Both fields are also perpendicular to the direction of wave propagation. Electromagnetic waves carry energy through space and are characterized by parameters such as wavelength, frequency, phase velocity, and intrinsic impedance. These concepts are important for understanding wave reflection and transmission. What is normal incidence? Normal incidence occurs when an electromagnetic wave strikes a boundary perpendicularly. In other words, the angle between the direction of propagation and the normal to the boundary is 0 degrees. This is the simplest case of wave reflection and transmission because the wave propagates directly towards the boundary without any angular deviation. Studying normal incidence helps us understand more complex boundary interactions. Next, we see about the types of boundaries. When electromagnetic waves encounter a boundary, the nature of the boundary determines the wave behavior. There are two important types of boundaries. The first is the conducting boundary, which has very high or infinite conductivity. The second is the dielectric boundary, which consists of insulating materials with infinite permittivity and intrinsic impedance. Examples of dielectric boundaries include air to glass, air to water, and air to plastic interfaces. Next, we see about the wave incident on a perfect conductor. Consider an electromagnetic wave travel toward a perfect conductor. A perfect conductor has infinite conductivity and does not allow electromagnetic waves to exist inside it. Therefore, the wave cannot penetrate through the conductor. As a result, the entire incident wave is reflected back into the original medium. This phenomenon is called total reflection. Next, we see about the reflection at the conducting boundary. At the conducting boundary, the incident wave reaches the surface and generates a reflected wave. Since no energy can enter the conductor, all the energy is reflected. The reflected wave travels in the opposite direction. The total electric field at any point is obtained by adding the incident and reflected fields together. Next, we see about the reflection coefficient at conducting boundary. The reflection coefficient indicates the ratio of reflected electric field to incident electric field. For a perfect conductor, the reflection coefficient is -1. This means the reflected wave has the same magnitude as the incident wave but undergoes a phase reversal of 180 degrees. Therefore, complete reflection occurs at the conductor surface. Next, we see about the electric field distribution. The incident and reflected electric field combines to form the total electric field. At some locations, the fields reinforce each other, while at other locations, they cancel at each other. This results in alternating regions of maximum and minimum field intensity. The resulting pattern is called the standing wave pattern. Next, we see about the standing wave formation. A standing wave is produced by the interference of two waves of equal frequency traveling in opposite directions. In this case, the incident wave and reflected wave combine to form standing waves. Standing waves contain fixed points called nodes where the field is zero and anti-nodes where the field is maximum. Standing waves are commonly observed in transmission lines and waveguides. The magnetic field at the conducting boundary. Unlike the electric field, the magnetic field at the conductor surface becomes maximum. The reflected magnetic field acts constructively to the incident magnetic field. As a result, the magnetic field intensity at the conducting boundary is greater than that of the individual waves. The behavior is important in understanding electromagnetic energy distribution near conductors. Next, we see about the power flow at the conducting boundary. The power carried by an electromagnetic wave is represented by the Poynting vector. Since the incident power is completely reflected, the average power entering the conductor is zero. Although energy exists near the boundary, power is transferred into the perfect conductor. This confirms that a perfect conductor does not absorb electromagnetic energy. Next, we see a numerical example for a conducting boundary. Let us consider a simple example. Suppose the incident electric field is 50 volts per meter. Since the reflection coefficient for a perfect conductor is -1. The reflected field is equal in magnitude but opposite in sign. Therefore, the reflected electric field becomes -50 volts per meter. The negative sign indicates the phase reversal. Next, we see the normal incidence at dielectric boundary. Now, let us consider a dielectric boundary. A dielectric material has finite permittivity and does not conduct electricity like a conductor. When an electromagnetic wave encounters a dielectric boundary, part of the wave is reflected and the remaining part is transmitted into second medium. The amount of reflection depends on the intrinsic impedance of the two media. Next, we see about the reflection coefficient. For dielectric boundaries, the reflection coefficient is determined by the intrinsic impedance of the two media. If the intrinsic impedance are equal, no reflection occurs. If they are different, a proportion of the incident wave is reflected. The reflection coefficient helps us determine the amplitude and phase of the reflected wave. Next, we see about the transmission coefficient. The transmission coefficient indicates the fraction of the incident wave that enters the second medium. It depends on the intrinsic impedance of the two media. A higher transmission coefficient means more energy is transmitted across the boundary. This concept is widely used in optical fiber and antenna design. Next, we see the cases of the reflection. Let us examine three special cases. First, when the intrinsic impedance are equal, there is no reflection. Second, when the impedance of the second medium is greater than the first medium, the reflection coefficient becomes positive. Third, when the impedance of the second medium is less than the first medium, the reflection coefficient becomes negative. These cases help predict wave behavior at boundaries. Next, we see a numerical example for the dielectric boundary. Consider a wave traveling from air whose intrinsic impedance is 377 ohms into a medium with intrinsic impedance 200 ohms. Substituting these values into the reflection coefficient formula gives a value of approximately minus 0.307. This indicates that about 30% of the wave amplitude is reflected while the remainder is transmitted. Next we see about the power transmission. The reflected power is proportional to the square of the reflection coefficient. The transmitted power is equal to the indicated power minus the reflected power. Engineers use these calculations to design efficient communication system and minimize signal losses. Finally, we came to see the application. The concept of reflection and transmission have many practical applications. Conducting boundaries are used in electromagnetic shielding, waveguides, and resonant cavities. Dielectric boundaries are important in optical fibers, antennas, microwave circuits, radar systems, and wireless communication. Understanding these principles helps engineers design efficient electromagnetic systems. Hope you all understood. Thank you.